Hello everyone and welcome to this presentation. Today we're gonna cover the rate of change of f of x, which is the directional derivative. This is basically the directional derivative is the rate of change of a function called f of x in the direction of a specified unit vector. So let's say we have a unit vector which is AB or ABC or 5, 4, 3. So this unit vector can be basically anything. If you can write on this. Okay, so we have here this unit vector. So if you can see it. Okay, we have this unit vector ABU. U equals AB. It can be also a unit vector of three components. So U equals A, B, C, or for example, V equals 1, 2, 3. These are all unit vectors. Can be three components, two components, or even is it possible to have one component? That's a good question. Can we have one component unit vector? Anyway, let's stick to the definition. The definition states that the directional derivative is the rate of change of a function in the direction of a unit vector. That's the definition of the directional derivative. And it's denoted by du. This is the derivation for, or the notion for the directional derivative is du f of x, and f of x can be any other function, any function of x and y. And the definition for the directional derivative is, as you can see here, it is the limit of f of x, plugging in the value for x, x plus ah. So ah is the difference, the delta h, like for the regular derivative. For the regular derivative, let's say here we have f prime of x. What is the definition of a regular derivative? It is basically f of x plus h minus f of x over h. Of course, the limit, we don't forget the limit. So, as you can see here, f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. So you can see the similarity here between the two definitions for a directional derivative and the regular derivative. So some similarities, but here we should note that in the directional derivative we have two variables, and therefore we're gonna plug in two rate of changes, or two h values you can call it, or whatever, like two differences, and these are gonna be different. So for the x is gonna be ah, for the y is gonna be bh. And if you can say ah, now we're gonna show you like a picture to demonstrate this, but basically the h vector is gonna equal ah I plus bh j. See, these are the unit vectors, and this is the h vector. We're going to show you exactly how is that. We're going to show you. So minus f of x, okay, over h. So this is the definition, the formal definition of the directional derivative. So, and there is, here we can see the proof for this, and how do we get finally um, a formula that we can use for any function to get the directional derivative, since it could be hard to compute the limit always using this definition. So you can see here that if we define a function of a single variable g of z equals f of x naught plus az and y naught plus bz, these are all the differences. then by definition, the derivative for the function of a single variable, this is, we are gonna use now the definition for this definition for a single variable, since we have only g of z. So it's gonna be g prime of z equals the limit as h approaches 0 of g of z plus h minus g of z over h. So this is exactly what we have here, but instead of g, we're gonna replace it by uh, instead of f, we're gonna have g, and instead of the variable x, we're gonna have z. So yeah, and then if we want to evaluate derivative at z equals 0, we're gonna just substitute z equals 0, and this is gonna give us basically g of h minus g of 0 over h, and of course the limit. And now if we substitute n for g of z, so you plug in um, g prime of z, we're gonna have this formula. So for that, okay, so this part is basically this part, g prime of 0, and then we have the limit, which is the definition. Okay, yes. So here, this is basically the definition g prime of x, but this is at 0, 0. So he substituted x naught, y naught here, and he used the limit definition of the directional derivative. So instead of x, we're gonna just plug in simply x naught, and instead of y, we're gonna plug y naught, and then same for here, and then this is like what do we get? This is the formula. So basically, this gives us the this gives us a formula for the directional derivatives at 0. Okay. Okay, so yes, this is, I wanted to show you this. It's important to see that here. First, let's focus on this region. Now, as you can see, this is the vector u that we have. First of all, this is a vector u. Let's say this vector is basically a component of two vectors, and of course, this is uh, the part in the orange, colored orange. This is the curve that we have, and we have here a cutting plane that is that includes the vector u, and the cutting plane is perpendicular or is parallel to the z-axis. So as you can see, this is the plane, and this is the z-axis. Okay, so the plane is parallel to the z-axis, or let's say yeah, it's parallel to the z-axis and perpendicular to both the x and y-axis, and also the plane should include the unit vector. So here, the unit vector u, what is it composed of? So first of all, u is h, u unit vector, and h is the length of the unit vector. H is the length of the unit vector, and u is just a unit vector pointing at the direction of u. So if we want to have the unit vector at the direction of u, we're gonna have just the unit vector over its value or its magnitude, and h is the magnitude of the unit vector. And if we want to write this vector in component form, we're gonna write u equals HA, okay, in the I direction as we wrote before, plus HB in the J direction. So HB in the J direction, and this gives us the unit vector, okay, which is simply also can be written as this AB, and this is what was given. Um, so this is the diagram, and basically this is what we are getting. And the directional derivative is the intersection between the plane that is perpendicular to both the y and x axis, the cutting plane, okay, and that which includes a unit vector. So the plane is gonna include the unit vector, is gonna be in the direction of the unit vector. It's gonna be perpendicular cutting the plane, and we're gonna have the directional derivative. This just erase everything. So let me explain to you what is the directional derivative in the picture. So like we know that in 2D the directional derivative is basically the slope in 2D. So let's say this is a function. Okay, this is a function f of x. If you want to find the slope at any given point, let's say point A, so we're gonna find the derivative, and the derivative at point A by is gonna be represented by this line. This is gonna be represented by this line. So m, the slope, is gonna be equal to f prime of A. If we want the slope at any point, let's say f of x, f prime of x at any point, then we're gonna need to differentiate f with respect to x. And here we can get the slope at any point, which is the derivative in this case. Okay, so going to 3D now. Now going to 3D. What is the derivative, the direction derivative in 3D? Or let's say, what is the derivative in 3D? In three-dimensional um, coordinate. What is the derivative there? The derivative is basically um, the same thing, but instead of having a derivative for, let's say, each line, we want to have now a derivative over. So in order to have a derivative, we need to have a curve. Here we do have a curve, but we do have a curved surface, not like a curved line. And for a derivative, we need a curved line. So this is a curved line. This one here, this is a curved line. Any function is a line, regardless if it's curved or straight line. But we need a line. We need a 2D line to have a derivative. Now in 3D, we don't have lines. So for that, we create a line by having a plane, this plane, cutting through the surface at a specific direction. We can have also maybe a different plane in this direction. See, we can have a plane in this direction, and I can call this direction V. So this plane is it includes the unit vector V. It includes the unit vector V. So now here I can have another directional derivative, which represents the slope of the intersection between the curve and this new plane. So this is the curve, this is the intersection, and the derivative, the directional derivative, represents the slope at this curve. And here, so in the direction of u, now in the direction of the vector u, we have this curve. Just change the color. So we have this curve in the direction of u. This curve represents the directional derivative for the vector u. So sorry, not the curve itself, but the slope of the curve. The slope of the curve is the direction derivative. The curve itself is just a function. It's a regular function. It's f of x, y, or say g of x, y, or z of x, y. Any, give it any name. The thing is that the directional derivative, the the direction of u, of vector u, of f of x, y, is basically the slope of this function. Basically what? The slope of this function. The slope of f of x, g of x, z of x, whatever. Now maybe someone would be asking, can I find the second directional derivative? Well, that's a good question, and we're gonna try to answer that. If not, we could have a different video for that. So, but now I wanted to focus on this specific problem, and also here you can notice some points PQ, and the vector U is basically it extends from P to Q. No, sorry, it extends from P prime here, P prime to Q prime, and these are all in the XY plane. Let's say an extension, or what do you call it? Like if you have a line, you extend the point downward to the XY plane, where Z is 0. We're gonna have then P prime and Q prime. So these are like projections, or you could say, of the point. Projections of the points here on the XY plane. These are gonna be PQ, and these are gonna represent also another way to represent U. We can say U equals um, Q prime minus, no, we can say P prime Q prime. Yeah, so P prime Q prime is just a line, and it's basically vector U. So, and this is the graph. Maybe if we continue to the proof, I would rather not, I would rather go to the questions, but if we continue to the proof, we can just simply see we stopped here. Now, we had the definition of the directional derivative in terms of the limit, but if we try to rewrite g of z as using a different, now this is a different approach to writing g of z. Now, let's say we have, again, a function g of z equals f of x. This is any function g of z defined in one variable, okay? And we are assuming that x equals x naught plus az and y equals y naught plus bz. Now, how did we get this? Well, we just define it this way, or maybe here we can say that from this and this we can get x and y. This is one way to approach it. But let's say that we just define it as x equals x naught plus az and y equals y naught plus bz. So now we can use what we call the chain rule. And basically, if you are not familiar with the chain rule in 3 dimensions, it's very simple. So if you have, now let's break this down. Okay, so let's say we have a function. We have a function, now we have, yeah, we have gz, a function of z, okay? And we want to find, and we have also z is a function of x and y, okay? And we want to find the derivative of g with respect to x. Okay, so we have g we have g in terms of z. This is any function, let's say z squared plus z, for example. This is this function, okay? And we have then z equals x squared y plus y. So this is z. It can be any function in terms of x and y. And now if we want to find dg with respect to the derivative of g with respect of x, we can basically, this is gonna be the partial derivative, of course, yeah, that was gonna be the partial derivative of g, yeah, yes, the partial derivative of g with respect to x. Is that right? I'm not sure. Anyways, let's stick with the definition until I clearly understand this. But basically, this is all proof, okay? And the formula is very, very, very simple. It's simpler than this. So basically, this gives us like, yeah, g prime of z equals fx. This is the partial derivative of f with respect to x, xy times a plus fy of xy times b. And this is basically the derivative of g from the chain rule. Okay, now if we take z equals 0, we'll get x equals x naught and y equals y naught. And this is just a definition. If we let z equals 0 and plug it in here, this is gonna equal to 0, equal to 0. So we're gonna have x equals x naught, y equals y naught, and this is what we get. And then, yeah, this is what we get. We get g prime 0 is this. And now if we equate this g prime of 0 with the results we got there, this, so, sorry, okay, so we said here g prime of 0 is basically the directional derivative, okay, and then if we equate this with this g prime of 0, we get that directional derivative. Now this is the definition. We got to the definition. That's it. So the directional derivative of f of x naught y naught is basically fx of x naught y naught times a plus fy x naught y naught times b. And this is the definition of the directional derivative. That's it. And a, b are just components of the unit vector u. So a, b. This is the unit vector u, and this is a, b. These are just the components. So we're gonna multiply. We're gonna first find the partial derivative of x of f with respect to x first. This is the partial derivative of f with respect to x, df over dx. It's basically this. And we're gonna evaluate the partial derivative of x at the point x naught, y naught. Okay, and this is basically this part. Then we're gonna find also the partial derivative of the partial derivative of f with respect to y, and we're gonna evaluate it at x naught, y naught, and gonna multiply it by b to get the directional derivative. It's very simple. The formula is very simple. You don't need to get very deep, and we can solve an example now, and maybe this just the formula itself is enough. So maybe you can get some space to solve the first example. So example one. Okay. So find each of the directional derivatives. So A, we want to find the directional derivative of f(20), where so the point is 20. Okay, we have the point 20. We want to find the directional derivative at this point, and we have the function. This is the function, and the unit vector is in the direction of theta equals 2 pi 3. So how are we going to find the directional derivative from the angle? Basically u equals cosine, so this is from the geometry, cosine of 2 pi over 3 sine of 2 pi over 3. Okay, and we can evaluate this. I think it's if I can get a calculator. So cosine of 2 pi over 3 is negative 1 over 2, and sine of 2 pi over 3 is root 3 over 2. Okay, okay. So in order to find the direction derivative, we can use some space here. Yeah, okay. Maybe you can do this and this, take this, save, let's go here, and let's insert this, that. This is our example. Let us solve A first. So first, let's write down the definition. What is the definition for the directional derivative? We said directional derivative of f of x in the direction of u, of vector u, is gonna equal to fx of xy, the partial derivative of f with respect to x, times a, plus the partial derivative of y, xy, times b. Also, if we have z, for example z, so it's gonna be fz. Of course, we need to have three variables. So if we want to have z, for example, let's say here u f of xy equals fx. Okay, let's say we have xy first. Yeah, we're gonna have z. Okay, if we have three variables, we're gonna have z a plus fy. It's just we're gonna add a term and gonna that no, we're gonna add the partial derivative of f with respect to z, x, y, z. Okay, and if we have four variables, we're gonna add also the partial derivative of the fourth variable. If we have five variables, we're gonna add the partial derivative for that, and so on. So this is how we do it. This is the partial derivative. Now let's solve our question. First, let's find the partial derivative for x. So the partial derivative for x of f with respect to x is basically given our function. The function is okay. So if we want to find the partial derivative with respect to x, it's gonna be basically e to the xy plus xy e to the xy. Okay, so we take y as constant and we differentiate with respect to x. So we have x and we have it as 1, and then we have xy e to the xy. Okay, so yeah, and y is just constant, so it's taken. Okay, and then we have fy. Okay, so the partial derivative with y is basically uh, it's gonna be x e to the x, so everything else is constant. So we're gonna have x squared. Yes, we're gonna have x squared because x is gonna be regarded as a constant. So e to the 2y, the derivative of that with respect to y is basically 2e to the y. And here we have, instead of 2, we have x. So yeah, so we're gonna have x squared. Okay, so x squared, and for the y is just gonna be 1. And these are the partial derivatives. Now, if we want to evaluate them at point P. Yeah, we want to evaluate them at just okay. Let's evaluate f of x at the point P, which is 2, 0. It's basically e to the 2. No, this is 1. So e to the 0 is 1 plus xy e to the xy. It's just 0 times 0 is gonna be 0, so it's 1. This yields 1. And if y equals, we're gonna have x squared. So the point is 2, 0. Okay, we're gonna have x squared, so we're gonna have 4. 4 plus 1 equals 5. And this is gonna be 1. X squared 2, 4. So 2, 0 plus 1. So fy is 5. Okay. So, and finally, directional derivative f of xy evaluated at the point 2, 0 equals 1 times a. What is a? We said the vector u equals negative 1 over 2 root 3 over 2. So this is, so the value of a is negative 1 over 2 plus fy 5 times root 3 over 5, which equals to negative 1 over 2 3 over 2 plus 5 root 3 over 2, or 5 root 3 minus 1 over 2, and that's exactly the answer. This is for the first part. So this is part A. We can go to part B and solve something here. Well, it's the same. Also, there's something we didn't cover before we go to part B. There's something called the gradient of xy, f of x, y, and it's basically the partial derivative of x, partial derivative of y. So it's a vector. Okay, so the gradient is a vector. Okay, it's a kind of vector function since these are two functions. So it's a vector function, or a function vector, call it whatever. So basically, for our example here, let's say part A, the gradient of f was e to the xy plus xy e to the xy and x squared e to the xy plus 1. And this is the gradient for f in our example. So this can be useful since we can directly multiply the gradient by the vector u, or the direction of u, which is this, and the direction of u is just u, the vector u divided by the magnitude of u, and this is gonna give us also the directional derivative. Yeah, so let's try use the gradient for our next example. We can illustrate this better. So let's say he wants the direction. So part B wants the directional derivative of f of x, y, z. Now see, there are three variables now. We're gonna show you how to do it. It's easy, just you add another term to the formula. And the directional derivative is gonna be in the direction of u, or in the direction of v. Okay, so now we want to find the direction derivative, direction of v. So let's write down the function f of x, y, z, function of three variables, x squared z. And please, if you do have any questions, please drop it down in the comments, and I'll try to answer you personally if I can. X, Y, Z. Okay, and we have V, which is a vector, equals to negative 1, 0, 3. Okay, so now this is the vector. Okay, now let's find first the gradient. Let's start with the gradient now. So the gradient of x, y, z is basically uh, this vector. So let's find the partial derivative with respect to x is 2xz plus taking everything else as constant um, and differentiating with respect to x, so yz, and then fy is the same thing, 3y squared z squared minus xy. Minus xz. And then f of z is just squared plus 2y to 3z minus xy. Now the gradient is basically, so did he give us a point? He didn't give us a point. So he wants the general directional derivative in the direction of v. So he didn't give us a point. So what can we do? What we can do here is that we can just generalize, substitute the functions. Minus yz, 3y squared z squared minus xz, and then we have x squared plus 2y to the 3z minus xy, and this is the gradient. To find the directional derivative of f of x, y, z, we gotta multiply the gradient. Gradient. Okay, this is the gradient. X, Y, Z. We gonna multiply it by v unit vector. Not the vector itself, the unit vector. So it becomes multiplied by v over the magnitude of v. Okay, so how can we do that? Let's find first, we can find the magnitude of v. So the directional derivative is basically f of x, y, z. Simply this 2xz minus yz. I'm gonna write the gradient 3y squared z squared minus xz x squared plus 2y to the 3z minus xy multiplied by the vector v, which is minus 1, 0, 3, divided by its magnitude, which is 1 squared plus 3 squared 1 plus 9 square root of 10, which gives us finally dv f direction derivative equals, so this is minus 1, so we're gonna have first 1 over 10 times yz minus 2xz. I'm multiplying this with this, and then multiplying this with 0, and then multiplying this with 3. So these go together. So then we have 0, so we don't write anything, and then we go 3x squared plus 2y to the 3z minus no 6 divided by 3, remember. Okay, 3xy. And do we have any terms that we can cancel out? Y, z, x squared? No, I don't see any terms that we can cancel. So there are no terms, so this is basically the general directional derivative of x in the direction of v. So now if I have any values, say I want the directional derivative at point 1, 2, 3, I can substitute in here, and this will give me the dv at the point 1, 2, 3. So this is the general directional derivative. Okay, let's see other examples we can solve. Do we have a couple of examples? Okay, so this is the definition of the gradient. If a function of two variables, x and y, if we have a function, two variables, x, y, then the gradient of f is the vector function. Yes, it's a vector function, delta f, uh, which is denoted by this. You can write in the vector form or also this form. Y, g. You can add maybe another k. We can add k, and this is what we said. The directional derivative of x is the gradient multiplied by the unit vector. This is the unit vector. Just be careful not to confuse it with the vector itself. And this is the definition that we covered. This is the formal definition of the directional derivative. So before we evaluate, and this is important, before we evaluate the derivative, we need to make sure that this limit also exists. If it doesn't exist, then we do not have a derivative. So, and this is then the way we can find it. Okay, so these are some more examples. More examples. Let's solve an example. Let's try to solve example 2 real quick. Since I think this video has become very long and I hope you don't get bored. You know, it's difficult to get bored with a class like this, math. Yeah, I feel you, I feel you. Uh, anyway, we need to continue with our lecture. Okay, so it's very easy. Just solve now. F of xy is gonna equal x cosine of y, and v is gonna equal 1. Now, he didn't give us a point, so he wants the general directional derivative in terms of xy. Terms of xy. So, let's use the definition, the gradient definition. So this is v. Okay, let's find directly the fx. Fx is just cosine y. Fy is minus x sine of y. Dv xy equals cosine of y minus x sine of y. You multiply it by 2, 1 over square root of 4 plus 1, so 2 squared plus 1 squared over 5. And this is the direction derivative. Now b, we have the function f x y z equals sine of yz plus ln x squared plus, okay, just that's it. And he gave us a point 1 1 pi, and give us the direction v equals 1 1 negative 1. And he is asking us to find the directional derivative of u f of, oh, that's different notation, vector x. Okay, vector. Okay, so basically, I think vector x here is just um, yes, it's just x y z, or can say I plus y j plus c k, maybe. Yeah, I think this is the same notation, so I'm just the definition f of the gradient x y z multiplied by, let's write it this way, again the vector is v. Okay. The vector is mu on this multiplication. So the gradient, it is with respect to x, is just 2x times 1 over x squared. This is for the x, and this can be simplified to 2 over x. X squared, yeah, 2x, and 1 over x squared. So this is 2 over x. And then, with respect to y, fy, we have cosine of yz. Z cosine of yz. And with respect to z, we have, now we're just solving some examples you can solve with me. With respect to z, we're gonna have y cosine of z, and this is the gradient. 2 over x, z cosine of yz, y cosine of z, multiplied by v, 1 1 negative 1 square root of 3. And this is the direction derivative. Okay, now going to our next topic. It's here, it's a theorem. So suppose there is a function f that's differentiable of 2 or 3 variables. So we can say that the maximum value of the directional derivative d of x is the gradient, the absolute value of the gradient and it occurs when u has the same direction as the gradient vector. So basically, what does this mean? If we have here u, and we have here the gradient vector of x, have here u, the angle between them is theta. Now what we are doing, we are using the dot product. We multiply f of x dot u, are basically performing the dot product direction. Okay, so this is the dot product, and the dot product is just say so the u of x, the definition of the direction derivative, okay, which is just basically is f of x, the absolute value, u absolute value, cosine of the angle between them, which is alpha. Now the absolute value of u, the unit vector here of that's in the direction. So if this is the vector u, this is the unit vector u in the direction of u, and the magnitude of it is just 1. So we can take it out. So we can say du f of x is basically the value of the gradient of f of x multiplied by cosine of theta. Now, if we want to maximize the directional derivative, we want to minimize cosine theta. No, sorry. We want to maximize cosine theta. And when cosine theta is max, it's max when theta is 0. 0 or, yeah, it's maximized when theta is 0. So when we have theta equals 0, du f of x is maximum. And what does theta equals 0 imply? It implies that u is in the direction of the gradient. So when the vector u is in the direction of the gradient, we get the maximum directional derivative value. And these are some examples. If you want to solve them, you can try them. It's basically the same. However, here we have instead of a vector, we have points pq. So in order to find the vector v, the vector v is basically pq, which is equals to so q minus 3 minus 2 is minus 5, 1 minus 0 is 1. So this is the vector v, and we're gonna solve it basically the same as we did for all the other examples. And also he wants the directional derivative of f at the point p, direction of from p to q. So the point is b, and the vector is minus 5, 1. Okay, let's try to solve this example. Don't want to take long doing this, but since this is an important example, so we need to solve it. Okay, so the example is this one. No, the one in red. This is the example. Okay, so let's solve A, part A. We're gonna find first the directional derivative. Now we're gonna find the gradient. So fx is basically 2x e to the negative 2y and then with respect to y x squared minus 2 e to okay, multiplied by the vector minus 5 1 divided by its magnitude 5 squared is 25 plus 1 square root of 26, and this is the directional derivative at any point. If we want to find the directional derivative at the point P, we're gonna just substitute the point P. Just 2 0 equals, substituting in give us 4 times 1 and 4 minus 8, so minus, this gives us minus 8 multiplied by minus 5 1 6. This is 4 times 5 minus 5 is minus 20 minus 8 over square root 26. It is minus 28 over root 26. This is the value of it. Now, for part B, so this is the value of the directional derivative of u of f in the direction of u. Now he wants us to find a unit vector in the direction in which it increases or decreases more rapidly, okay, at p, and find the rate of change of f in that direction. Okay, so okay, so we want to find a unit vector in the direction which it increases or decreases more rapidly. We're gonna find the rate of change of f in that direction. Okay, so I think it's just the vector over its magnitude. Since there is no cosine theta, we're assuming cosine theta is 0. So I have another value that's going to be different. Okay, so it decreases more rapidly in this direction, which is minus 5 1 over square root of 26. And this is the direction which is negative 5 over root 26 and 1 over root 26. This is the unit vector. The unit vector, okay. And if we say this is the unit vector at which the rate of change increases more rapidly at point B. So I need you to practice also with me because practice is very important for, you know, understanding. It's not only watching me solve this. So if we want the one which decreases more rapidly, when are we going to have a decrease? Like a rapid decrease, the most rapid decrease. What do you think? Now the cosine function starts at 1, goes to 0, goes to negative 1, then back to 0, and so on. So when do we have the most negative value? It's here. It's here. This is the most negative value. We have -1, which occurs at 270 degrees, or pi over 2, 3 pi over 2 in radians. So which is basically the negative of this vector. So when u equals just the -26 over 20. Let's check this. I do have my today's class notes. Yeah, today's class notes. Okay, so we found the directional derivative but didn't find the rate of change. So I'm not sure, but I think what he did was right. So yeah. Okay, moving on to the next topic. So here we have gradient vector is orthogonal or perpendicular to the lever surface. What's the lever surface? F of xy equals k at point x naught y naught. Let's see. Now we see this in a graph. Likewise, the gradient vector f is orthogonal to the level surface f of x y z equals k at the point x naught y naught z naught. So I have two variables and three variables. Let's see. And this is a fact. Okay, let's see what does this mean. Now we have this photo. They have this picture, this illustration. So okay, interesting. Now let's see. So let's assume a curve, any curve. This curve has a function f of x, y, z. This is a curve. Okay, and we have now a point P, any point P at the curve, and on a specific directional derivative. So if we're gonna imagine a plane like this, extending and intersecting with the curve. And then we can imagine also a different curve plane which is tangent to point P. And here r prime of t, this is just the directional derivative. So r prime of t naught is at point P. Okay, this is the directional derivative. Directional derivative. Huh. So, and what is this stating? This stating that, what is the fact that we just read state? Basically states that the gradient is always perpendicular to the tangent plane at at a specified point. So, and this is basically a fact, is orthogonal or perpendicular at the level curve. Level curve is like the directional curve, or the directional derivative curve. This is the level curve, and yeah. So this is basically the tangent plane is the level curve, is the tangent plane to the level curve at point P or at any point. So the equation of this tangent plane is okay, yeah. And if we want to find the equation of the tangent plane, we can say f of x, this is a mistake. So f x naught y naught z naught, x minus x naught plus fy, this is the, of course, partial derivative with respect to z, respect to y, to respect to x naught y naught z naught, y minus y naught, and fz, x naught y naught z naught, z minus z naught. And also we can find the symmetric equation of the normal line. Normal line. the suit. Okay, so these are, yeah, this is the symmetric equation of the normal line. Okay, yes, this is a different illustration. Surface S. Okay, let's go this way. See, the gradient is always perpendicular to the surface, especially specifically the tangent surface at the point. And this is just the derivative. This vector is the derivative. X not y not. So find the equation of the tangent plane. Find the equation of the tangent plane and normal line to the hyperboloid. To the hyperboloid. Okay, okay. Solve this. Oh, getting tired. Getting tired. Okay. So this is the equation for the tangential plane. We can say that fx, can write it small fx, x naught, y naught, z naught times x minus x naught plus fy x naught, y naught, z naught, y minus y naught, and then plus fz x naught, y naught, z naught multiplied by z minus z naught. Okay, we do have all of this. We just need to find the fx, which is from the function from the hyperboloid. Just hyperboloid. Okay. So how do we find? We need to find the the the, the fraction, the partial derivative with respect to x. And to do that, we need f. Yeah, I think it's just if we say 0, yeah, I can say f of x, y, z is equals to basically x squared minus 2x squared, z squared minus 2y squared minus 12. Okay, and then we differentiate this. Okay, so differentiating this gives us minus 4x, 4x, therefore I give us minus 4y, and fz gives us 2z. Okay, and so first we substitute the values of x, y, z at this point P, 1 minus 1, 4. So if we put 1, it's gonna be minus 4 times x minus x naught, which is 1, plus substituting minus 1 gives us 4 times times y plus 1. Then we gotta multiply by 4, we're gonna have plus 8 z minus 4. And this is the equation of the tangent plane. Yep, this is the equation of the tangent plane. Ooh. Let's check. Okay, yes. Okay, so this is the picture. You can see that the gradient is also in the direction of the normal line. The tangent line here, as you can see, uh, minus 4, 4, 8. Okay, I think we got it. I think we got it. X minus 1, y plus c. Oh yeah, we equate it to 0, that's it. That's what I needed. Just equate it to 0. And this is basically the equation of the tangent line. That's what I needed. Okay. Yes. Oh, sorry, the tangent plane. That's the equation of the tangent plane. And for the normal line, we can just say tangent plane. This is the equation of tangent plane. And then for the normal line, we can even simplify it by saying minus 4x plus 4 plus 4y plus 4 plus 8z minus 8 times 4 is 68, 32 minus 32 equals 0. Adding this all gives us 8 minus 32 minus 8 is just a 20. I can't count, but 24. Okay, it's just 24. Okay, and then for to get the, is it 24? I think it's 24. Yeah, he did solve it. But yeah, anyways, and for the for the normal line, we can write it in the parametric form. So x is, the point is 1 plus or minus 4 minus 4t, y equals 4 is from minus 4 is from here, and then we have minus 1 plus 4t, and then for z we have 4 plus 8t, and that's exactly it. This is the equation of the normal line. Let's check, and that's the equation of the normal line. See, this is the level curve, and this is the gradient, and this is the directional derivative. Are some couple of examples. Here, this is an example of finding the gradient. We did that. Finding the directional derivative. Finding a symmetric equation. Okay, this is an interesting question. Okay, this is the same. Let's find this, use this. So this, do an example of this. And this is our final example. We're gonna be done with this. Okay, let's take a picture as usual. As usual. Oh, directional derivative. derivatives. Such an amazing thing. Do you love derivatives? I personally love derivatives. I love math in general. Even though it have not made me any money yet. I hope it does. If it doesn't, then, well, wasted time and energy at least. But it's all for the passion, you know? Okay. Okay, so let's find the symmetric equation. Let's copy the equation of the symmetric equation. X minus x naught over fx x naught y naught z naught equals y minus y naught over fy x naught y naught z naught equals z minus z naught over fz x naught y naught z naught. So do we have a point? Yes, we do have a point. This is the point, just writing in white. Okay, and we have also the equation of the ellipsoid and hyperboloid. So he wants us to find the intersection between these two curves. How are we going? Whoa. How are we supposed to find the intersection? So it's a bit weird. So an ellipsoid is basically, let's show you an image of an ellipsoid. Try to imagine how is this going to intersect. So ellipsoid, spell it right. Okay. So this is an ellipsoid. It's like a sphere, but like it's not symmetric. It's like the Earth. Looks like our Earth. So yeah, it's like an ellipse but in 3D. So that's why the name ellipsoids. So this is our ellipsoid if we try to imagine it. Okay, an ellipse. Okay, and then we have the hyperboloid. Let's show you the hyperboloid. The hyperboloid. This is the hyperboloid. It's like a cone. Yeah, and the cone, you know, like two cones put together. Then we have a hyperboloid. Like this is the shape of the hyperboloid. So it's gonna be something like this. You can say hyperboloid. Okay, and then the intersection is just basically here. So it's gonna be a bit weird, the intersection. It's gonna be, of course, 3D, so something like this. Maybe a smaller hyperboloid. Not sure. We need to graph this, but basically we need to find the intersection for this. And in order to do that, let's see how was this done. Okay, so these are the two equations. Okay, so in order to find the intersection, we need to perform we need to do cross product. One second. Yeah, we need to do cross product. Okay, we need to do cross product of the gradient for f and g. So we need to find the gradient for both curves. Okay, that's our goal. Our goal is to find the gradient for both curves. Okay, in order to find the gradient for both curves, we first do the following. First, let's define f of x, y, z, okay, equals x squared plus 4 y squared plus 2z squared equals 27. Then we have g of x, y, z. It's another function. X squared, minus 27 equals to 0, okay. And then we have x squared plus y squared plus z squared minus 11, which is equal to 0. So in order to find the gradient of f, we are going to just Also, we can simply find the gradient at a specific point, which is 3 minus 2, 1, since we only need it at this point. So first, or let's find the regular gradient first. Okay. So the first, the regular gradient is gonna be just 2x, 8y, 4z, and then for g we have 2x, 2y, 4z. Evaluating at the points, at the given point, 3 minus 2, 1 gives us 6 minus 16 and 4. Evaluating at the point, minus 2, 1 gives us 6 minus 4, 4. Now cross product f cross by g so I, j, k. So since these are vectors, so we're gonna cross product. So cross product basically gives us like a perpendicular vector to both of these. Okay, so 6 minus 16, 4. 6 minus 4, 4. Okay, I think there is a mistake here. This should be minus 2. Okay, since this would not give us hyperboloid if it's positive, so it should be minus. And now we just do the cross product. Let's do it for the I. Just 6 times 4 minus 6 times 4. Just minus 48. For the j, is 6 times minus 4 minus 6 times 4. It's also 48. Is it? Interesting. Okay, so 6 times minus 4 minus 6 times minus 16. Finally, we get 72. This is for the, is it? No. 72, yes, 72. Okay, this is for the gradient. Basically, that is the, slope. This is the intersection. Yeah, this is the intersection. So what do we do with this? Okay, so now, yeah, now this is the vector, the slope of the vector. So in order to find the symmetry equation, we just use the point we were given, which is 3. So we say 3 minus 48t, y equals, this is right, it's 48t, and z equals 1 plus 72 t. I hope I did not make a mistake. Okay, no, yes, I'm correct. Yes. But here it's 80. Why? Is it really 80? Minus 16 times minus 4. It's 4 times minus 4. 48 now. This is 48. Oh no, actually it's 80. It's 80 here. Come on, is it 80 or not? Yes, it is 80. It is 80. Okay, so just a calculation mistake, but overall the answer is correct. Or the way to solve it is correct. This is the way to correctly solve it. And that's that. Thank you for watching. I hope you benefited from this. Thank you very much.